Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Alhamdulillah Rabbil Alamin. Wassalamu ala Sayyidina Muhammadin wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wa uqdatan min lisani yafqahu qawli wa zidna ilma wasna rahma Allahumma inna fi ta'wil. Alright, welcome back to Technique class. Inshallah today we will continue our chapter on chapter 1. Okay, at the last class, previous class, we had looked at viscosity, we had looked at drag force, and also we had looked at the shear stress and shear force. I hope you still remember what is shear stress and what is shear force. Okay, today we'll be looking at the example for shear stress and shear force. Okay, this is example 4. Okay, in example 4, what we have in example 4 is a 35 mm diameter shaft is pulled through a cylindrical bearing as shown in the figure. Okay, this we have a bearing, we have a shaft, and the shaft is pulled inside a bearing. Okay, we have a shaft and then we have a bearing. So this bearing. Okay, we have bearing, and we have shaft. Okay, the shaft is pulled by a bearing. Okay, the bearing shown is in the figure. Okay, the lubricant that fill the gaps is 0.42 millimeter. Okay, between the shaft and the bearing. Okay, the viscosity of the oil in the bearing is 8.3 times 0 minus 4 meters square over second. Okay, this is a kinematic viscosity. So what is kinematic viscosity? This is kinematic viscosity. Kinematic viscosity is nu equal to mu over rho. Okay, what is mu? Mu is the viscosity. Mu is this viscosity. Okay, alright. So let's look back at the equation. Okay, and the specific gravity of the oil is 0.93. Okay, determine the force F required to pull the shaft at a velocity 3.4 meter per second, assuming the velocity distribution in the gap is linear. Okay, we have a shaft. We have a shaft here, and the shaft is inside a bearing. Okay, the shaft is inside a bearing, and they pull the shaft at velocity 3.4 meter second. Okay, they said that the shaft has the diameter of 35 mm. Okay, and the bearing is 0.5 meter wide. Okay, what else we have? We have 0.2 gap between the shaft and the bearing, and we have the kinematic viscosity and the specific gravity. Okay, we have the gap here is the gap. Okay, the gap between the shaft and the bearing is 0. The gap here is 0.42. 42 is 2. Sorry. 0.42 mm, and we have the kinematic viscosity of the oil is nu equal to 8.4 times 0 power by minus 4. Okay, we have meter square over second, and then we have the Sg of the oil, specific gravity of the oil is 0.93. Okay, I assume this is correct. 8.3, sorry, it is 8.3. Is 8.3. Okay, assume this is correct thing. Okay, alright. So we then want to know the force that require to pull the shaft at 3.4 meter per second. Okay, what kind of force is needed here? So the force that needed to pull the shaft is the shear force, since we are dealing with the fluid. Okay, shear force, what is shear force? Shear force equal to mu du dy or times A. Okay, what is mu du dy? This is actually stress, the shear stress is tau. Is tau. Okay, this question, A is unknown to us. Du is the velocity of the shaft, so we already know 3.4. Dy we is already known 0. Okay, the gap is 2 mm, but you need to change into meter. So, okay, change to meter. And then we have mu. So mu is also unknown. So how we calculate mu? So we know that mu, the kinematic viscosity, is given to us 0.3 times 10 minus 4. Okay, so mu is equal to mu over rho. Okay, mu. So mu is equal to mu times rho. So nu is already known, is given to us 8.3, but rho is unknown. So you need to find the rho. How we find the rho? From Sg. We have Sg here. So Sg, what is Sg? Sg equal to rho over rho H2O. Okay, rho over rho H2O. Rho H2O is always 1000. 1000. Let's remember 1000. Okay, so to find the rho equal to Sg times rho H2O. So the rho is 930 kilogram over meter cubic. Okay, so just insert the value of rho here and you will find mu, and when you find mu you can insert it here. Okay, now for the A is the area. So where is the area that we should take? The area here or the area that cover around the shaft. So which area that covered by oil? Okay, this area, for example, area 1 or area 2. Area 2 is covered by oil, but not area 1. Okay, area 2 yang kena minyak. Okay, kena minyak area 2 saja, area 1 tak kena. Okay, so how we calculate area 2? Simple, 2 pi r. Why we using 2 pi r? Because you just want to know the circumference of the shaft. Okay, times y dia lah berapa? We already know the y is 0.5. So time the L dia berapa? 0.5 meter. And we got the answer. Itulah. So R, where you find R? We already know that the diameter is 0.35. Okay, from here you can find R and then calculate the A2. Okay, A2 here, area around the shaft. Okay, and then you can calculate the FT, which is shear force. So this is your first homework. Okay, your first homework, calculate the value of shear force. Okay, all right. Now let's continue to the second example, which is example 5. Okay, in this example we have two parallel surfaces separated by a 40 millimeter gap. Is filled with a fluid of viscosity 0.3834 Newton second over meter cube meter square is the dynamic viscosity, which is mu lah. Okay, assume the flow velocity varies linearly. Determine the force needed to move a thin plate, negligible the thickness. When the plate is 10 mm above the bottom surface, the plate area is 0.53 meter square and it moves with a velocity 0.5 meter per second. Okay, we have a plate. Okay, moving between a gap. Here we have here a gap. Okay, alright, that's correct. Okay, two parallel surface, right? To have surface, two parallel surface, and we have a plate here moving between the. Okay, then moving, the plate is moving at 0.5 meter per second, 0.5 meter per second. Okay, the gap between the surface is 40 mm. Okay, the surface is 10 mm above the bottom surface. Okay, and then we have the mu. Okay, the mu is 0.34834 Newton second over meter square. And then we have a plate area 0.53. The area of plate is A, 0.53 meter square. And then we have the gaps and then 10 meter above the surface. Okay, so the question is to determine the shear force. Okay, shear force is the same question as before lah. Okay, alright. Okay, so what is shear force? We had looked at before. Shear force Ft equal to mu du dy times A. Okay, mu is already known to us. They given us the mu. U is also given to us, which is 0.5. dy, okay, A area already given to us 0.53 meter square. Okay, but dy, you have 2 dy. Why you have 2? We have 10 meter and 30 millimeter. 10 millimeter and 30 millimeter. Why we have 2? Because the plate is square. And the plate have upper surface 1 and a bottom surface 2. So we have 2 surface for the plate. Okay, we have upper and the bottom. So Ft should have 2. You should have 2 Ft, which is Ft1 plus Ft2, and then we have the total of Ft. Okay, the total force, the total shear force of Ft. You need to calculate Ft1 plus Ft2. Okay, what is it? So Ft, for example, we have Ft1 equal to mu is the same, du dy is this, du is the same, A is the same, but dy is different. We have 10 millimeters dy and another 10 millimeters, 10 millimeter, and we have another one, Ft2 equal to mu is the same, du is the same. Okay, we have A is the same, dy, we have the one is 30 millimeter. Okay. Okay, you need to change the unit into, always remember, always change unit into SI. Okay, always change your unit into SI unit. Okay, so calculate the total force, total shear force that required to put a plate at 0.53. So this is your second homework. Second homework. Okay. So let's continue our chapter here. We have done example 1, example 2. Just need to calculate the equation that I given to you. Okay, so now we'll be looking at the fluid flow field. Okay, we have two types of fluid flow field to represent the fluid flow. One is Lagrangian, and we have Eulerian. Okay, what's the difference between Lagrangian and Eulerian? Okay, what's the difference between these two? Okay, for example, we have here we have Euler, we have Lagrange, we have Euler, we have Lagrange, Lagrange, okay, and yin G, Euler, yin. Okay, we have two. Okay, what is the difference between these two? Okay, first of all, we look at the Lurian description. Okay, what is Lurian description? Here we have a table, pool table. Okay, individual object. Okay, in the Lurian description of a fluid flow, a finite volume called a flow domain or control volume is defined. Using Eulerian, we define a few variables, function, or space and time within the control volume. Okay, this is Eulerian. Okay, the field variable at a particular location, a particular time is the value of the variable is whenever a particle happen to occupy location at a time. Okay, alright, this is Lurian. Okay, Lagrange. Where is Lagrange? Oh, they don't have any Lagrange here. Okay, to put it simply, what is Lurian and Lagrange? Okay, for example, we have a pipe. Okay, we have a pipe. In this pipe, we have water. Okay, we have water. We want to study the fluid properties in this pipe, which is water lah. Okay. Okay. When we have water molecules. Okay. When you are using you are using. Okay, we are the same way Lagrange. So we also have water molecules. Okay, when you are using Lagrangian concept, we are looking at the velocity and the vector of every single molecule in the water. If you want to study the water properties, you have to look at every single molecule. What is the velocity? Where is the vector of this every single molecule? It's very difficult to track all of the molecule. Okay, very difficult to track every molecule in the pipe. Okay, in this pipe. Okay, but if you're using Eulerian concept, we are making a control volume. We call it control volume here. So we are not looking at the velocity and the vector, but we are looking at the properties inside the control volume, such as density, okay, such as the temperature, such as the pressure, okay, inside this control volume, okay, which is much easier than the Lagrange concept, where you have to look at every single molecule, the velocity and the vector. Okay, that is the difference between Lagrange concept. In Lagrange concept, we are using CV, or we call it just control volume. Control volume. But in Lagrange concept, we are looking at the individual particles, okay, which is impossible to do. Okay, all right. So this is between this is the difference between Lurian and Lagrange concept. Okay. Okay, next. Okay, all right. So we are looking now flow pattern. Okay, in flow pattern we have streamline, stream tube, path line, straight line, and timeline. Okay. Okay, what is the streamline? Okay, tengok sikit apa itu streamline. Okay, streamline and stream tube, very simple. Streamline, a curve that is everywhere tangent to the instantaneous local velocity vector. Okay, just streamline is just a curve. Okay, a curve everywhere tangent. Okay, everywhere in this streamline is tangent. So we have, for example, we have a pipe. Alright, we have a pipe. Okay, for example, the part is have water inside it, and we can look for a streamline. Okay, streamline. We can find streamline in part. Okay, the stream is moving like this. Okay, for example, everywhere the streamline is tangent. Okay, tangent means that the tangent lah, the tangent dekat sini tangent. So this is a straight part. You should have a curved part. Because, for example, we have a curved part. We have a curved part, curve part. Okay, inside this part we have a streamline of water. Okay, streamline of water. Okay, streamline of water. Okay, the streamline of water. Every single curve, every single curve here, curve here, curve here, the tangent. Okay, the tangents means kat sini dia ada streamline. Okay, right? A curve that is everywhere tangent to the nearest locus velocity. So the streamline here is just a line. Actually, it's not just a line. Okay. Alright, and then what is string tube? Consists of bundle of streamline, much like a communication cable consists of bundle of fiber optic cable. Okay, to put it simply, what is string tube? Okay, a string tube is very simple. If you have a streamline 1, okay, when we have a streamline 2, and we have another streamline 3, streamline 4, and we have another streamline 5, 6, and so on. Okay, the streamline make a tube. Okay, make a tube. So they call it string tube. Okay, we have a here tube. Tube make out from streamline. Okay, make out from streamline, so we call it string tube. Okay, very easy. And then we have path line. Okay, what is path line? Path line is very simple. So very simple. Okay, for example, we have a particle A moving from point 1 to point 2. So the particle is moving like this. Okay, the movement of the dot here is the path line of the particles. Okay, and if the particle is moving straight like this, then we have another path line. Or we have the particle moving like this with curve, and then we have another path line of the particle A. So this is path line. Okay, so next one we are looking at the straight line. Okay, what is straight line? The locus of fluid particle that have passed sequentially through a prescribed point in the flow. Okay, very simple. So we have here before we have particle A. Now particle B also moving using the same path line. Okay, particle C also moving the same path line. D also moving the same path line. So now the path lines become the straight line. Okay, they become the straight line. So that's the difference between the path line, straight line, string tube, and streamline. Alright, and what is another one? Last one, we are looking at the timeline. So what is timeline? It's very simple. For example, we have here a part. Okay, we have a part, and we have particle 1, particle A. At T1, particle is here, and at T2, particle A is here. So this is the line of T1 and T2 is we call it the timeline. Okay, at T3, particle A is moving at T3 here. Okay, so this is the timeline for particle A at T3. Okay, that is okay. Basically, in word, a set of adjacent fluid particle that were marked at the same earlier instant of time. Okay, so the set equal a set, so we have a lot here. Okay, timeline T1 we have here, T3 here, T4 here, maybe at T5 it become congested here, maybe. Alright, so that is the timeline. Okay, classification of fluid. Okay, here we are looking at the classification of fluid, whether viscous or inviscid. Okay, what is viscous? Viscous flow in the friction effect are significant. Okay, inviscid means that in many flow particles interested and the region typically rigid, not close to the solid surface. Okay, very simple. So what is inviscid and viscous? So for example, we have a surface and we have water flowing over the surface. Okay, so which area is viscous, which area is inviscid? Okay, the area that close to the surface is the viscous area. Okay, viscous area, and the area that away from the surface here at the bottom, is we call it inviscid area. Okay, we have inviscid and the area. Okay, this is inviscid area, this is viscous area. Okay, further from the surface is inviscid, closer to the surface is viscous area. Okay, alright. So internal, external and internal flow is very easy. Okay, what is internal? If the flow over the surface, we call it external. If the flow, for example, we have pipe here. Okay, the flow is moving inside a pipe, so it is internal flow. Okay. For example, for the fluid that is external is water in the drain, water in the lake, water in the river. Okay, that is an external flow. Okay, internal flow is water in pipe, water in duct. Okay, duct. You know duct? D-U-C-T. D-U-C-T. Yeah, D-U-C-T. Duct. If pipe is circle, duct is triangle lah. Okay, right triangle, right triangle. Alright, so that is between external and internal flow. Alright, we have compressible and compressible. Okay, compressibles, very simple lah. Compressible is something like a gas. Okay, gas. Okay, incompressible is like water. Water is compressible. For example, we have a bottle of water. You can compress the bottle of water because the fluid inside the bottle is incompressible. But if you only have a bottle that have no water inside it, you can compress it very easily. Okay, because the inside the bottle is air, only air. Okay, alright. That is the difference between the incompressible and compressible. Okay, alright. Now, okay, lamina, viscous, lamina, turbulent, and transitional flow. Okay, what is different? Okay, very simple. For example, we have here lamina, and we have here transition. Okay, transition, and we have here turbulent. Okay, lamina, a flow that have a orderly streamline or straight line. Okay, transition, the flow that move in S, which S here like this. It is transition. Okay, turbulent, the flow that in this order, the movement of flow is in this order. Okay, okay, how to differ it? The higher the velocity, okay, the higher it is low velocity, higher velocity. If the velocity is higher, and then the flow is moving towards turbulent. Okay, and we have another one here is Reynolds number lah. Is Reynolds number. Okay, how we different lamina, transition, and turbulent through velocity and Reynolds number. Okay, Reynolds number. I will teach you later lah what is Reynolds number. Okay, just remember that lamina is orderly, moving in orderly fashion. Transition moving in S movement of orderly fashion. Okay, and turbulent is disordered. Okay, disordered. Alright, disordered. Alright, and then we have. Alright, that's all for our class today. So that's the end of our chapter 1. Okay, well, I will make another example on the chapter 1 in another video. So I hope you remember that you need to solve the homework problems, homework 1 and homework 2, is submit it. Okay, is in the time given. Alright, that's all for our class today. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.